Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So, in the previous module we had seen transmit beamforming in a MISO system, that is multiple input single output wireless communication system, right. But we said one of the challenges in transmit beamforming is that we need to know the channel state information at the transmitter, which is a challenge in a wireless communication system. So, from a practical perspective, we also want to look at schemes when the channel state information or the channel coefficients, the knowledge of the channel coefficients is not available at the transmitter, and for that purpose we are going to look at a new scheme which is termed as space time coding, which is a very popular MIMO wireless transmission scheme. In particular, we were going to look at a special case of the space time code which is immensely popular, also known as Alamouti code, right. So, in this module we were going to focus on what is known as the Alamouti. We are going to focus on the Alamouti code, which is a space time block code, a space time which is a space time block code, which is a space time block code for, and this does not need channel state information or knowledge of the channel coefficients, that is unlike transmit beamforming does not need knowledge of the channel coefficients at the transmitter. Hence, this is very useful from a practical perspective or from a practical viewpoint. This is, so what we are saying is this Alamouti is a space time block code which is a transmission scheme for a MISO system, specifically for a 1x2 MISO system, and this does not need the channel state information at the transmitter. Hence, it is a practical scheme, it is useful from practical perspective for practical implementation in a wireless communication system. All right. So, let us start by considering, to explore this Alamouti scheme, consider a 1x2 MISO system. One cross 2, as we already seen, which means R equals 1, T equals 2, that is number of receive antennas equals 1, number of transmit antennas is equal to 2. Therefore, we have the system model Y is equal to H1, H2, X1, X2 plus W. This is the system model that we have. We are considering a 1x2 MISO system, 1 receive antenna, 2 transmit antennas, and this is the system model that we have. What we are going to do now is we are going to consider 2 transmit symbols X1 and X2. So, now what we are going to do is consider two symbols X1 comma X2. Now, in the first time instant, that is in the first time instant, what we are going to do is transmit transmit as follows. What we are going to do is x1 is transmitted from transmit antenna 1 and x2 is transmitted from transmit antenna 1 and x2 is transmitted from transmit antenna 2. So, what we are doing is in the first transmit instant, our transmit vector is given as x1, x2, where x1 is the symbol that is transmitted from transmit antenna 1 and x2 is the symbol that is transmitted from the transmit antenna 2. Therefore, the symbol received y1 is given as I have y1 is equal to h1 h2 x1 x2 plus w1. So, what is this? This is the symbol received at transmit instant 1 or the first time period. So, y1 is the symbol that is received at the output of the first transmission period in this Alamouti coded MISO system. Now, what are we going to do in the second transmit period is something interesting. In the second transmit period, we are going to transmit the same symbols x1 and x2, but from the first transmit antenna, we are going to transmit minus x2 conjugate, and from the second transmit antenna, we are going to transmit x1 conjugate. So, in the second transmit period, for the second transmit period, what we are going to do is we are going to transmit minus x2 conjugate from the first transmit antenna. So, this is from transmit antenna 1 and x1 conjugate is transmitted from transmit antenna 2. Therefore, at the receiver y2, that is the symbol output. What is y2? y2 is the received symbol after the second transmit period equals h1 h2 times minus x2 conjugate x1 conjugate plus w2. So, we are transmitting minus x2 conjugate from the first transmit antenna, x1 conjugate from the second transmit antenna. Therefore, the symbol received is y2 equals h1 h2 times minus x2 conjugate x1 conjugate plus w2. This is the system model for the second transmit period. Now, let us look at this, let us expand this slightly. I have y2 equals h1 y2 equals h1 x2 minus x2 conjugate x1 conjugate plus w2, which I can expand as minus h1 x2 conjugate plus h2 x1 conjugate plus w2. This is what I get expanding this. Now, I can take the conjugate of y2 at the receiver. Y2 conjugate is minus h1 conjugate x2 plus h2 conjugate x1 plus w2 conjugate, where we use the property that a b conjugate is a conjugate times b conjugate. which is equal to basically now I can also write this as H2 conjugate x1 plus H1 conjugate times minus x2. I am just rewriting this as H2 conjugate x1 plus H1 conjugate into minus of x2 plus W2 conjugate, which is equal to, now I have H2 conjugate H1 conjugate H2 conjugate H1 conjugate. In fact, I can write this as minus H1 conjugate x2. So, minus H1 conjugate into x1 x2 plus W2 conjugate, correct. And therefore, now I can write, now I have simplified this as y2 conjugate equals H2 conjugate minus H1 conjugate, the row vector, times x1 x2 column vector plus W2 conjugate. Let me rewrite this again. So, now I have two equations. From the first transmit period I have y1 equals H1 H2 times x1 x2 plus W1. From the second time period I have y2 equals H2 conjugate minus H1 conjugate x1 x2 plus W2 conjugate. Now, I can combine these two into a single equation. Therefore, I have y1 y2 conjugate is equal to H1 H2 H2 conjugate minus H1 conjugate x1 x2 plus W1 W2 conjugate. So, now what I have done is basically I have stacked y1 and y2 conjugate, and what I have received is I have received an effective system model for this Alamouti coded system, in which I can represent these various quantities now as this quantity here, this is y bar, which is a 2 cross 1 vector. This quantity here, this is a 2 cross 2 matrix. This quantity here is my transmit vector x bar, and this quantity here is the noise vector w. This quantity here is the noise vector w bar. I can also now denote by, I can denote this column of this matrix by C1 bar, the first column, the second column of this matrix by C2 bar, and therefore, what I will have now is y bar equals C1 bar times x1 plus C2 bar times x2 plus w bar, right, where C1 bar is the first column, C1 bar equals H1 H2 conjugate, and C2 bar is the second column, C2 bar equals H2 minus H1 conjugate. So, these are the two columns of the matrix, right, these are the two columns of the matrix, and also w bar as usual is the noise vector, is in fact the Gaussian noise vector. W bar is a Gaussian noise vector with IID, independent identically distributed noise elements, which means the mean is 0, variance of the noise element is same, and the correlation between the two different noise elements is 0. So, I have noise elements which are IID, which means independent independent identically distributed noise elements, the mean is equal to 0, the variance is equal to sigma square. So, I have these two columns, I have C1 bar is H1 H2 conjugate, C2 bar is H2 minus H1 conjugate. Now, let us observe an interesting property of these columns C1 bar C2 bar. So, if I look at these two columns, I have C1 bar equals H1 H2 conjugate, I have C2 bar equals H2 minus H1 conjugate. Now, let us observe an interesting property. Observe that C1 bar Hermitian C2 bar is, if I observe C1 bar Hermitian C2 bar, C1 bar Hermitian is transpose and take the conjugate, that is H1 conjugate H2 times H2 minus H1 conjugate, which is equal to, now you can see this is H1 conjugate H2 minus H2 H1 conjugate, which is equal to 0. Therefore, if I perform this operation C1 bar Hermitian C2 bar, I get 0. So, C1 bar Hermitian C2 bar, or the inner product between these two columns of the matrix is 0, which means C1 bar and C2 bar are orthogonal vectors, because C1 bar Hermitian C2 bar equals 0, it means the dot product or the inner product between these two vectors is 0. Therefore, these two vectors are orthogonal. So, these vectors from a geometrical perspective, these vectors are C1 bar comma C2 bar, C1 bar comma C2 bar, these are orthogonal, and this is an interesting property of the Alamouti code. Therefore, Alamouti code, since C1 bar and C2 bar are orthogonal, Alamouti code is also known as, you will also hear Alamouti code called as an orthogonal, it is an orthogonal space time Alamouti code is an orthogonal space-time block code, or basically it is an OSTBC. This is a very interesting property of the Alamouti code, where the column vectors C1 bar and C2 bar are orthogonal. Therefore, the Alamouti code is also known as an orthogonal space-time block code. Now, let us look at the receiver for this Alamouti code, and the receiver has a very simple structure. I have Y1 bar equals C1 bar x1 plus C2 bar x2 plus W bar. Now, therefore, if I look at C1 bar Hermitian divided by norm C1 bar times Y bar, that is equal to C1 bar Hermitian divided by norm C1 bar times C1 bar x1 plus C2 bar x2 plus W bar, which is equal to C1 bar Hermitian C1 bar divided by norm C1 bar x1 plus C1 bar Hermitian C2 bar divided by norm C1 bar x2 plus C1 bar Hermitian W bar divided by norm C1 bar. Now, if you look at this first quantity, the first quantity is C1 bar Hermitian C1 bar, which is norm C1 bar square divided by norm C1, this is equal to norm C1 bar x1 plus the second quantity, look at it, C1 bar Hermitian C2, but C1 bar Hermitian C2 is equal to 0. So, second quantity is 0 plus C1 bar Hermitian W bar divided by norm C1 bar. So, therefore, what we get is essentially we get an interesting equation, norm C1 bar times x1 plus C1 bar Hermitian W bar divided by norm C1 bar. I can call this as my noise W tilde, and what we have seen is because C1 bar and C2 bar are orthogonal, simply by projecting along C1 bar or beam forming along C1 bar Hermitian divided by norm C1 bar, I am able to remove the interference that is caused by symbol x2 at the receiver. Similarly, I can do for decoding symbol x2, I can multiply by C2 bar Hermitian divided by norm C2 bar, and since C2 bar and C1 bar are orthogonal, that will remove the interference that is caused by symbol x1, and I can thus decode symbol x2 at the receiver. Now, let us look at the property of this noise W tilde. So, now let us look at the property of this noise W tilde equals C1 bar Hermitian divided by norm C1 bar into W bar. We have already said that W bar is IID Gaussian noise elements, that is the noise vector contains IID Gaussian noise elements. Therefore, the noise covariance expected W bar Hermitian equals sigma square times identity. We have already seen this, since the noise covariance, remember in one of the earlier lectures, in one of the beginning lectures on MIMO system, we said that when the noise elements are IID means 0 variance sigma square, the noise covariance is sigma square times identity. Therefore, the variance of this noise W tilde, if I look at the variance of this noise W tilde, that is W tilde times W tilde conjugate or magnitude W tilde square is equal to expected value of C1 bar Hermitian divided by norm C1 bar times W bar Hermitian times C1 bar divided by norm of C1 bar, which is equal to, now taking the expectation operator inside, I have C1 bar Hermitian divided by norm C1 bar times expected W bar Hermitian times C1 bar divided by norm C1 bar, and this is equal to 1 divided by norm C1 bar square times C1 bar Hermitian. Expected W Hermitian is sigma square times identity times C1 bar. So, I have C1 bar Hermitian times identity times C1 bar, which is equal to norm C1 bar square. So, sigma square norm C1 bar square divided by norm C1 bar square, which is equal to sigma square. So, what I am finding interestingly, that the variance of the noise W tilde expected magnitude W tilde square, which is equal to expected W tilde conjugate, this is also equal to sigma square. So, the noise variance or expected magnitude W tilde square is sigma square. Therefore, now going back to my system model, what I have is that is after I perform C1 bar Hermitian divided by norm C1 bar times Y bar, what I receive is basically norm C1 bar x1 plus W tilde, where W tilde is Gaussian noise of variance is equal to sigma square. This is Gaussian noise of variance sigma square. Therefore, the SNR is now equal to norm sigma 1 square times expected value of magnitude x1 square divided by sigma square. This is the SNR. SNR is equal to norm C1 bar square times expected value of magnitude x1 square, where x1 is the transmitted symbol, divided by sigma square. Now let us look at this quantity norm C1 bar square. You can clearly see norm C1 bar square is equal to norm. Well, first let us see what is C1 bar. C1 bar, recall C1 bar is simply equal to H1 H2 conjugate. Therefore, my norm C1 bar square equals square root magnitude H1 square plus magnitude H2 conjugate square, but magnitude H2 conjugate square is magnitude H2 square. So, this is magnitude H1 square plus magnitude H2 square, which is nothing but, I am sorry, there is no square root here, this should be or not. Let us look at norm C1 bar, and this is equal to norm of H bar. Therefore, my SNR equals norm C1 bar square expected magnitude x1 square divided by sigma square, which is the same as norm H bar square P or norm H bar square expected value of magnitude x1 square divided by this quantity sigma square, where sigma square is the variance of the noise. Now what we have to do is we have to find out this quantity expected value of magnitude x1 square or the power in the transmitted symbol x1, and this can be found as follows. Let us look at the transmit vector. The transmit vector here is x1 comma x2. So, therefore, what we have is we have two symbols in each transmit vector. So, we have two symbols in each transmit vector. Therefore, if the total power is P, this transmit power P has to be divided between the two symbols. Therefore, each symbol x1 and x2 will have half the transmit power or P by 2. Therefore, if transmit power is equal to P, if Tx power is equal to P, then expected value of magnitude x1 square equals expected value of magnitude x2 square is equal to P by 2, that is each symbol has half that is if the total power is P, then this power P has to be divided between the two symbols equally. Therefore, the power in each symbol is P by 2 or expected value of magnitude x1 square is equal to expected value of magnitude x2 square, which is equal to P by 2. Therefore, the final SNR for this Alamouti coded quantity Alamouti scheme SNR is norm H square expected value of magnitude x1 square divided by sigma square, which is equal to norm H bar square P by 2 divided by sigma square, which is equal to half norm H bar square P divided by sigma square, which is the same SNR as a maximal ratio combining SNR as MRC, that is the same SNR except for factor of so we get half the SNR that we get with maximal ratio combined. And this is very interesting because remember previously we had seen that in a maximum ratio, that is in a transmit beam forming system, we get the exact identical SNR as a maximal ratio combining system, right. So, in that sense transmit beamforming yields a performance that is exactly identical to maximal ratio combining, alright, but transmit beamforming requires channel state information at the transmitter, which is challenging. Now, what we are saying here is that Alamouti code does not need channel state information at the transmitter, but it achieves half the SNR as that of maximal ratio combining. So, the price that we are paying for not having the channel state information at the transmitter is that we are losing a factor of half in terms of SNR, right. So, basically in terms of the log scale, we are losing 3 dB, right. So, the SNR in an Alamouti scheme is minus 3 dB, is 3 dB lower than that of the maximal ratio or the transmit beamforming scheme or the maximal ratio combining scheme, correct. So, 3 dB is the loss in the Alamouti coded scheme, but it is practical, it is effective from a practical perspective because we do not need knowledge of the channel coefficients. And what you can see here is we have this factor of norm h square, which means the diversity order is preserved, therefore, the diversity order of this scheme is still 2. Therefore, despite the loss of 3 dB, despite not having the channel state information at the transmitter, it still yields the same diversity order as that of the maximal ratio combining based system. Alright, so this is the interesting property of the Alamouti code, and with this what we are going to do is we are going to conclude this module, and we are going to look at the other aspects, notably the bit error rate performance of this Alamouti coded system in the subsequent module. Thank you very much.